recording. So today what I want to do is I was intending to move on to talking about oxidations and E2s, and I realized that, there's a couple of things that we've kind of had holes fall through. So I want to go over a bunch of different concepts today. So it's kind of like a grab bag of things to do with E1, E2, SN2, and talk briefly about some alkyne chemistry as well, which plays nicely into the SN2 and E2 chemistry before moving on. So it's, entitled More Details and Some Alkynes. There we go. So what I want to talk about first is I want to talk about Hofmann eliminations. So we've discussed the Hoffman elimination, and this is when you have either an E1 or E2, when your base, nucleophile, but the nucleophile is acting as a base, and the base goes for the most accessible hydrogen that gives you the least substituted double bond, which is not the stable product. And the reason it does that is because it can't get to the other hydrogen because it's too crowded. So if we think about this, let's just consider an option. Let's consider this molecule here. I'm just going to draw a little bit lower down the page because I'm going to draw a reaction coordinate diagram above it. So I'll talk about that too. So we have this. So if you're, in an eliminating kind of mood and you're not clicking too quickly so that your icons aren't getting small, you'll notice that you've got two alpha hydrogens. So these are hydrogens on alpha carbons. Remember, this is the alpha carbon. It's adjacent to the carbon with the functional group. That's what we're looking at. And we can eliminate either one and we can get two products. If we eliminate the one on the right, we are going to go to this double bond. This is our Hoffman product. We eliminate the one on the left. We go to this double bond, and this is our Zaitsev product. So how do we get one or the other? Well, we choose our base. So let's think about this on a reaction coordinate diagram. So here's our starting material. Here's this product. Here's this product. Here is energy going up. And reaction coordinate is this way. Note that I can kind of go both ways on the reaction coordinate. It's not a one-way path. It's kind of two-dimensional. You can go forward and back in time, or going left and right as two different reactions. So if your base is a Zaitsev type of base, so what do I mean by that? Well, this isn't a great leaving group. It's a secondary leaving group, so we're probably going to favor E2. If I want to eliminate, I'm probably going to prefer doing E2 elimination to an E1 because it's not a great carbocation I'm making. So you're following that argument, you're going, okay, E2, Zaitsev elimination. Let's pick a Zaitsev type of base. Put up my chat window. In PDF, right? So, okay, I'm just going to pull back to the questions in the chat because I ignored Nulia's comment, which was in PDF for the SciComm. You can submit it in PDF. You can submit it in image like JPEG or TIFF. That's fine. As long as I can read it on a PC. So the only thing you're not allowed to submit is some retarded Macintosh program file that I can't read. And the one I run into constantly is Pages. I'm sure they have a PowerPoint version of that or something that I can't read. So if you are using those kinds of Mac programs, please convert to a PDF. The next assignment goes live. The next movie assignment goes live midnight tonight. This is the last one. I'm going to make an announcement. Thank you. I actually should have started with the class with that. Tahira, thank you. It's in the syllabus, goes live midnight tonight. It's on mechanisms because that's all we've done. And reactions. Reactions and mechanisms. Very specific. So stuff leading up to Monday's class inclusive, I think. And again, the SciComm assignment is due tomorrow, but there is no penalty if you submit it before the exam. Because they need to have a due date. Tomorrow, I think, tomorrow or Friday is my last due date possible. The Mobius is due midnight Friday. You got 48 hours as always. So you have all Thursday and all Friday. No, there's no lab test. You've been tested enough on a lab. Amen to that, Nicole. I do thrive on undergrad tiers, Victoria, but I can't get them live here. So, like as a vampire, it doesn't work well virtually. It says due 30th on the blackboard. Is that the SciComm, Sarah? Yeah, it's. I think when I think when I had that, I got slapped on a wrist by my head of department saying you're not allowed to have anything due in the last 2 weeks. So don't do that. I went, okay, so I'll make it due the 26th with no penalty till the exam, and I'm allowed doing that. So it's due to like I can't say it's due December 12th. I'm not allowed saying that. But there's no difference if you hand it in tomorrow or December 11th. You will get it's going to be graded after the exam. So if you need more time on a SciComm assignment, great. If you are ready to submit it, great. I'm really excited by some people who have run some really cool ideas by me. There's really, really cool ideas in this class. It's fun. Mobius is due Friday midnight. Just to be absolutely clear, it's due Friday 11:59:59. Because if I said it's a little ambiguous if I said it to 12:00. I'm worried that it would make it due Thursday midnight if I did that. And if you don't submit it for that reason, for some reason, it auto grades it for you, whatever you have done. Okay. Okay, so let's say we have a Zaitsev base, and we're going to come back to the Zaitsev versus Hoffman bases. This is one of the places where I am going to give you a rule, and it is a rule, and it's going to work for this class. This is Zaitsev base. The products are the products. The energy of the products is the energy of the products. So in a Zaitsev base, what's happening here is our transition state going to the more stable product is lower than the transition state going to the less stable product. That makes sense. If the product is less stable, you think anything leading to it is also going to be less stable. If the product's more stable, things leading to it should be more stable. Unless something else happens. And this is what happens when you have a Hoffman base. So let's say we switch bases to a Hoffman base. Now suddenly I'm really bulky. And this product is still this product, but this transition state would involve, to attack this hydrogen here, would involve it getting awfully close to this thing. That's really crowded. So suddenly this transition state spikes in energy. Because suddenly I don't have a really good way to get that big, bulky base in there. So I'm not changing the energy of the products when I'm going Hoffman versus a Zaitsev. What I'm doing with a Hoffman base is I'm making that transition state really difficult to approach. Now it's going to make this guy a little bit harder too, but it's going to be lower. And now what we've done is we've inverted which transition state is lower. And now we go to this product with the Hoffman. So that's why Hoffman bases do what they do and Zaitsev bases do what they do. Okay, great. How do I so somebody asked me the really smart question, which is, how do I tell if something's a Hoffman base or a Zaitsev base? This is how you tell. You refer to this list. And this refers to both these molecules and their neutral species. There's another one which we're not going to see very much of. I'm just going to put it on here in case. No, I'm not going to use LHMDS. No, it's for this class. It's all that. There are other ones that exist that are relevant for this class. The Hoffman is the less stable double bond. Yeah, these are all balls. They're huge. Everything else is Zaitsev. Yeah, there's two lone pairs. Nitrogen. I've really scrambled that poor guy. I don't know. It's got lots of dots. Yeah, both are E2s, but they're E2s removing different hydrogens. Everything else is Zaitsev. Okay. Then we have things that really want to be nucleophiles. So these are things where, we're saying the same molecule could be either a base or a nucleophile. That's really true of all the oxygen species. But there are some things which are just really shitty bases. So we saw lithium aluminum hydride and sodium borohydride when we did reductions. And if we think about what those carbonyls are, they're actually nucleophiles, and they're nucleophiles attacking the carbonyls. They're nucleophiles here too. So these guys are always nucleophiles. They're not great at displacing halides though. On epoxides, they're nucleophiles. Do not react with halides. In general. That's these two. So azide and cyanide are nucleophiles always. They're never reacting as bases. Iodine, chlorine, and bromine tend almost or always nucleophiles. So I'm gonna put a dot. I can't think of any examples off the top of my head where they'd be acting as bases, but they can conceivably act as bases, and we see them occasionally mop up extra hydrogens after a reaction. Is that DIPEA, both neutral and reactive? This is DIPEA. It's always neutral because you can't make it negative because you'd have to remove a carbon chain. There's no hydrogen to remove, so you can't have N minus there. Because it's a tertiary amine. Yeah. So our magic nucleophiles, you see azide, you see cyanide, you know you are doing substitution. You see a halogen coming in, you know you are likely doing a substitution. You see sodium borohydride, lithium aluminum hydride, you're looking for epoxides, you're looking for carbonyls to reduce. The oxygen guys are the ones that are really on the fence. Everything that's in the Zaitsev group, all nitrogen, oxygen kind of systems, they can be either. Actually, also in the nucleophiles here are the Grignards. This can be a base, but not E2, E1. Methyl magnesium bromide, these are Grignards. Now they can react. When we were doing the Grignards, we saw they react with carboxylic acids. That happens with the Grignards, but they don't react with, they don't do E2 reactions, they do substitutions. All other oxygen plus sulfur plus nitrogen. And everything in the Zaitsev thing can be a nucleophile, it can be a base. Everything in the Hoffman thing is not only a Hoffman base, it is never a nucleophile. Because if they can't even get to an exposed hydrogen, there's no way they are getting to a crowded carbon. Yeah, yes, exactly, Victoria. When it acts as a base, it becomes positively charged. So it's not a strong base. Now, where I want to go from this is I want to talk about an example with a ring. No, don't do that, you piece of garbage. There we go. So we have a reaction here. We have potassium isopropoxide in isopropanol, and we make that by taking a chunk of potassium and dropping it into isopropanol. Smokes a bit, creates some hydrogen gas, maybe a little bit of a fizzing. If you're unlucky, a bit of a fire because you set your hydrogen gas on fire. And we toss that in with the thing. Nulia, DIPEA is this guy, this thing I drew. Okay, so let's think about this. Now, your temptation, hopefully, is to be looking at that and going, okay, I've got a primary halide. I'm thinking about that. I'm going no carbocation, primary halide. I've got isopropoxide that is a strong base. It is an O minus. So SN1 and E1 are unlikely because the SN1 and E1 occur when the SN2 and E2 can't. The SN1 and E1 are slow. So the only time they happen is when the SN2 and E2 do not happen. But you've got something reactive. And so you should be thinking, oh, I like how Mohammed's thinking. Good, you're ahead of me, Mohammed. You should be thinking, okay, I'm not doing SN1, E1. There's no carbocation here. It's primary. I've got negative things. So I'm thinking SN2, E2. I'm looking at my base. I'm going, isopropoxide's a little bit bulky. It's primary, probably mostly E2, maybe a bit of SN2. But you remember what Mohammed has said in chat on November 25th, and that's that acid-base reactions are fastest reactions. And he's right. Compared to E2s, SN2s, just stripping protons off heteroatoms is like the fastest thing possible. And do we have a proton on a heteroatom that's acidic? And yes, we do. We've got no H on this molecule. Now, this often doesn't do anything if you do this. It's not productive. But in this case, it is. So you got an O minus. Now, we need to think about what that O minus can do. And if we go back to our ninjas, blindfolded ninjas in a room, this blindfolded ninja is attached by rope to a nice target there with a great leaving group on that carbon. They are attached together. This is a likely reaction. Yeah, see, Andrew's on there too. Now, the way we can figure out if it does the intra is we're counting the number of atoms that will be in the resulting ring. And if it's a reasonable number, like 5 or 6, 7 if we're feeling lucky, the intra is going to be a lot faster than the inter. 1, 2, 3, 4, 5, 6. I like 6. And we have the intramolecular reaction. So it's something to keep an eye out for on these. And actually, this gets used a lot to do a lot of chemistry, and you can get pretty unreactive things to behave properly when you can do them intramolecularly like this. Oh, okay. Um, if the ring is not between 5 and 9, would both be correct. I think you'd start seeing much more inter. I think what maybe if it's not, the question would be what is the to be if I'm okay if I'm answering this realistically, like not sort of a theoretical. This is a second year intro organic class where we can have strict rules. What I would actually say is I'd ask one of my students how concentrated is your reaction, because if your reaction is really concentrated, then you would get a lot more inter because there'd be a lot of molecules floating around. If your reaction is really dilute, you don't have very many molecules per volume of solvent. Even if that rope is really long, the ninjas are more likely to cut the ninja attached on a rope than another ninja if it can't find another ninja. So it is concentration dependent. It's just you don't really have values for that. So if I was looking for that, I might say extremely dilute or extremely concentrated. So from the example, it's 5. I don't know what the 5 refers to. This is a 6-membered ring. And the 5 and 6, it's really hard to stop them forming no matter how concentrated you have your sample. It's just the thing, it's just the way it wants to sit. It wants to sit kind of in a ring, and they just kind of fold in on themselves and do it. I think those are the key. Yeah, six atoms is what matters. How many atoms are in a ring? The oxygen's in the ring. It's part of a 6-membered ring because it doesn't change the bond angles are determined by how many members are in the ring, not how many carbons. And what we're trying to do is minimize that ring strain that we were discussing so much about back when we were talking about ring strain. And that's why 5 and 6 like being formed, because we don't have 8 and 9 don't form very quickly. And I think when we went back to that, we talked about the different energies of those, and those are getting higher energy. I don't understand why it jumps up so. Why there's a huge jump from 7 basically always going intra to 8 normally preferring inter, and it doesn't seem like a big difference to me. But chemistry disagrees with me, so obviously I don't understand. It's just you have one more degree of freedom, and that just screws everything up. And nine's even worse. So 5 forms fastest, then 6, then 7, then 4, then 8, 9. 3 is a little weird because it really depends what's going on with 3. 3 can form very, very quickly, as we've seen, or very, very slowly. Problem with 3 is it's often reversible because 3 is normally pretty unstable. Like this is very stable, but an epoxide is the 3-membered ring. That's very unstable. That's going to open up pretty easily. And actually spend some time opening those things up. So although it forms, it falls apart. Okay, so what I want to talk about now is I want to talk about alkynes. So alkynes are weird. So all the chemistry that we talked about with alkenes works with alkynes, except you do it twice. So if you take this molecule and you treat it with HBr, no surprise. Well, hopefully no surprise. There's already H on there. And then it probably reacts with another equivalent of HBr because there's HBr around. And of course, we have a resonance structure with the bromine, which can stabilize the carbocation. So not only is it secondary versus primary, it's also resonance stabilized. And so we get the second bromine coming in, the same site as the first one. Shouldn't be a surprise to anyone. So alkynes do alkene chemistry, they just do it twice. An interesting version of this is, I don't know if it's really an interesting version, but it's an outcome of this. So I treat that with a strong enough acid and base or water. It needs to be pretty strong. What I'm going to get, just from analogy with what we just did, yeah, I'll go back. Sorry, Ishida. Thank you for, I probably moved too quickly. Thanks. You good? Okay. Good. So acid and water, we create the more stable carbocation. That's on a more substituted carbon, hyperconjugation, blah, blah, blah. Why does it make the double bond? That's just resonance with the bromine. We're just stabilizing the carbocation. I'm showing that we can stabilize the carbocation with resonance. It's not the product. It's just you can stabilize it with resonance. It's shitty resonance because bromine doesn't particularly want to be positive. It's also shitty resonance because bromine is so much bigger than carbon, but so the orbital overlap is kind of crap, but it's still resonance. Okay, we're going to shuffle an H plus around here. I'm going to take one off the water. I'm going to put one on a double bond. If we think about where that is, it's going to want to go next to the OH. That's our new H over here. There's two others on that carbon. I'm just highlighting the one we just added. But now, of course, same rationale that we just had with the bromine, except now it's oxygen. So yeah, that's a resonance structure. But of course, we have another way to resolve this instead of bringing another water molecule, and that's that we can take away this proton. And oh look, we just made a ketone. So the alkyne doesn't, so where we got the dibromide with the alkyne, we get a ketone with water, which makes sense. It's two bonds to oxygen to the same carbon. And the best way to make two bonds to oxygen is a carbonyl, not two separate oxygen atoms. I'm trying to eat mandarins while lecturing. This is not working because then my mouth is full. Okay, my mandarin will have to wait. So, those are getting good. Normally, they're clementines, not mandarins. They're good a little bit early this year. Normally, I wait until December to buy them. But COVID makes us all act kind of crazy. So, yeah. So we can make acetone this way. So this is something I think about with these triple bonds. Now, there's two things that triple bonds do that double bonds don't do. So if I take a triple bond and I treat this with hydrogen and palladium. So if you remember right, and some solvent, it doesn't really matter. I'm going to use ethanol. If you remember from when we were talking about double bonds, what this did was the two hydrogen atoms added from the same face. I'm going to do that again. And then because now we have a double bond, we're going to add two more hydrogens from the same face because that's what it's going to do. So I'm going to sketch in, that they're up, previous two are down, and we have our two carbon chains. And so hydrogen on palladium reacts with triple bonds to take them all the way down to the alkane, just like it takes the alkene to the alkane. Now, there is a magic reagent. It's called Lindlar's catalyst. Along with hydrogen gas, H2. I'm just going to spell Lindlar in like block letters. Yeah. So Lindlar is poisoned palladium. What it actually is, I have no idea what the poor son of a bitch grad student who had to figure this out was. It's palladium on cesium carbonate instead of on carbon, poisoned with lead and quinoline. Quinoline is, you don't need to know this. You don't even need to remember that it's all this stuff. I'm just going to write Lindlar. But this is what it is. Quinoline's that. Nobody knows how this works. We've known about this now for about 100 years, and no one really understands how this works. Obviously, what happens is the palladium is kind of poisoned by the lead, cesium carbonate, and quinoline, so it's interacting with it. And what we're doing is we're deactivating the palladium, so it's less reactive. So what this does is it takes us to the alkene, and we stop. And you need hydrogen gas in here too. I do not understand this. I won't even pretend to understand it. It works amazing. It really, really works. Now, Kevin asked, would Lindlar ever work with an alkene? It doesn't tend to at ambient pressure. Now, if I throw 1,000 atmospheres of hydrogen on this, oh yeah, it'll work. But I can control it to make sure it doesn't if I want to. Jason, I have no idea. I don't know. You know, um, I'd say 1,000 monkeys slapping on 1,000 typewriters, but 1,000 graduate students slapping with 1,000 chemicals. Um, for all I know, it was a mistake. Like somebody was trying to do something, and their reaction was contaminated with lead, and they had some quinoline in there as a functional group, and the reaction didn't go with the palladium on carbon. And then they went, "Well, that's weird," and then they tried again, and it still didn't work. I have no idea if this is the story. And then they kind of isolated what things they needed to do to make it not work. They probably removed the quinoline. Hey, it worked. Put the quinoline back in. Stopped working. Um, this is one of those things where you just go, "Hey, that's weird," and it leads to new discovery. So this is something unique to alkynes. There's a way to do trans as well, transalkenes from an alkyne. We're not going to do that here because it just involves silicon, and I don't like silicon. There's some new modern catalysts to do this, but the modern catalysts cost a lot of money. We've got Lindlar on our shelf in our lab, and that's what we use. So this is one thing that's unique to alkynes. The other thing that's unique to alkynes is you can deprotonate them. Okay, so what I want to do is compare this versus this. Yeah, it really is. As an organic chemist, I'm very upset by silicon in general. It's really useful. Um, if I don't trust it. Okay. Let's take both of these, and we're going to treat these with really strong bases. I'm going to pick the strongest base I know. Terbutyl lithium. This is a lot of fun. It catches fire no matter what you do. Like you stick a syringe into it, it catches fire. You ever expose this thing to the atmosphere, it catches fire. So you have to be really, really careful when you work with it, so you don't set everything on fire, because it basically burns the air. But it's a really, really strong base. And that's because it's a freaking C- on a tertiary center. And you want a plus on a tertiary center. You don't want a minus. And you've got a minus on a tertiary center. So it's a really unhappy C-, and it's going to react. It's called T-butyl lithium. So it's going to remove a proton. So let's think about this guy. What it's going to remove is it's going to remove one of these protons. Why? Because when it does that, we did resonance. Yay, resonance. Everyone loves resonance. I love resonance. I really don't care what you guys think. This isn't a democracy. Okay. That's awesome. That's really resonance stabilized. And this is called an alloanion because it's allo and it's an anion. It's really not very creative. We move over to this guy. That's not where you're thinking is by analogy. And so far we've done everything in alkynes by analogy with alkenes except for that Lindlar thing. You would remove one of the hydrogens on here. And you'd be wrong. So what you actually do is you remove the hydrogen on the end of the alkyne. And you don't even need that strong a base. You can actually get by with a much weaker base than this. And there's actually a whole lot of really cool modern chemistry, which is really driven by the fact that alkynes are pretty easy to deprotonate. And it's completely changed everything about how we do biology and synthetic biology. And a lot of what I do relies on the fact that alkynes are easy to deprotonate. And it allows us to label cells and track probes through proteins and figure out what's reacting with what and where a cancer is. And it comes down to basically this fundamental idea that that proton is really acidic. A normal, just for relevance, methane, I think at the beginning of the class we talked about this, its pKa is about 45. Alkyne is about 25. So it's 10 to the 20 times more acidic. That's a lot. That's a lot more acidic. And the reason for that is this is in an sp orbital. And an sp orbital looks a lot more like an s orbital than a p orbital. Or it looks 50-50. It looks more like an s orbital than sp3 orbital. Just going into that dozy. Wouldn't it be better to have an anion on a secondary prime carbon and a 3' because of the hyperconjugation? I'm not sure I completely understand. On a secondary versus a tertiary? Yeah, it is. So this is primary is the best place. Best anion. Okay anion. Bad anion. So because it's such a good base because it's so reactive because it's such a bad anion. Okay. But in this case, not only is it primary, it's also sp, where everything else here was kind of sp2 in this case, or sp3. And sp is so much like an s, and that means the electrons are close to the nucleus, and the nucleus is where the positive charge is, and so bringing the lone pair close to the nucleus is good. That's the explanation I've always been sold. I don't know if I believe it, but I don't have a better one for you. So I'm going to stick with that one. The other argument I like is that if the electrons are in an sp orbital, that's kind of far away from everything else because it's kind of pointing away from everything else because it's sp, not like sp3 where everything's 109.5 degrees. It's 180 degrees from the other sp orbital. So it's far, those electrons are very far away. So they're less in the way of everything else. Yeah. Yes, Victoria, exactly. It's exactly the opposite. So Victoria said for carboanions, primary, best, secondary, okay, tertiary, horrid. Exactly. It's exactly the opposite of the carbocations. Because the reason for the carbocation stability is hyperconjugation because of the donation of the adjacent bonds into that empty p orbital. But now that p orbital is full and it's trying to find a place to go. And all it's got is big, giant filled orbitals around it, and it hates it so much. Yeah, you have to take my word for it. I'm sorry. I am going to go to authority. We can always go back to the argument that they're closer to the nucleus and the nucleus is positive, so the negative closer to the nucleus is good. Fine, I'll hand wave and we'll pretend that that's true. I just don't think it explains a 10 to the 20 difference in acidity. That just doesn't strike me as enough. Anyways, alkynes, negatively charged. So what does this mean? Why should any of us care about alkynes being negatively charged? Well, you should care because I care. And so we can have something like, got an alkyne minding its own business. We've got an alkene minding its own business. We take the alkene, we treat that with MCPBA. I'm going to make this an asymmetric alkene. That's going to make an epoxide. Take the alkyne, I'm going to treat that with a base. One of the bases we've seen is LDA. What is that? Lithium diisopropylamine. So we saw it as one of our Hofmann bases. Very hindered, very strong, and minus. So it doesn't set fire to things quite in the same way that C minuses do, so it's a little bit safer. About 35 is the pKa. So we have a negative charge there. Then this acts like a nucleophile. Think about, again, we're going back to this nucleophile E2SN2 reactions, and we want to talk about, it does something look like a stick or not. You don't get much more stick-like than an alkyne. Like two of the examples where I said these things are always nucleophiles were azides and cyanides. And what they have in common is they're very sticky. You got an sp3 sp hybridized atom with the charge on it, and that makes everything else tucked in way behind it, so its A value is tiny. And alkynes are the same thing. Everything is tucked in behind. It's an sp hybridized. These are great nucleophiles. So you got a great nucleophile, you got an epoxide. We are clearly under basic conditions because we got a freaking C minus in the house. And so we are going to attack the least hindered side of that epoxide. Whee! And it's an SN2 reaction because there is inversion of configuration. And it, of course, is an SN2 reaction. So when we were talking about epoxide openings earlier in the course, and even all the openings of chloroniums and bromoniums, those three-membered rings, those were all SN2 reactions. We didn't call them that at the time, kind of glanced over it, and we said, hey, it comes in from the backside. It is just an SN2. So all of those opening of three-membered rings we did are SN2 reactions. Because it's stick-like, less hindered, but we're under basic conditions, and so there's no particular reason to attack the more hindered or less hindered site. They're kind of equal electronically. So remember when we're opening an epoxide, if this was OH plus, if this was charged, then it would be a bigger delta positive on the tertiary and a smaller delta positive on the secondary. And so we'd be attracted to the tertiary because of electrostatic attraction. We're under basic conditions. So there's no delta positive on either of those carbons really. So even though this is a small cat, you're small and it could fit through a small door or a big door, it's going to prefer going through the big door. It's just easier. You're always going to aim for the biggest door you can if everything else is equal. And in this case, there's no preference for either door. They both lead to the same amount of kibble. And I'm starting to worry that my analogy is going to get me into trouble here. So basic conditions attack the most accessible version of the epoxide. And so we end up with this. So if I scroll back a few slides, more slides, more slides, more slides, more slides. We can add alkyne anions to this nucleophile. Yeah, you finish everything off with a proton. It's kind of like French chefs with butter. Finish everything with butter. Yeah, so what we would do is we would work this up with water. Yeah. You're not just always neutralize stuff once you've done everything you think you can. And so we get that. Okay. So we've talked about alkyne chemistry. I think we talked about what I really want to hit on with nucleophile electrophile chemistry, which is some things, the Hofmann bases are the big, really bulky ones. Everything else is a Zaitsev base. There are some things which really prefer to be nucleophiles and bases. Then we discussed intermolecular versus intramolecular reactions. We really like that 5 to 7 range for the intra. Inter, everything outside of that, except if something's really, really concentrated. And then we talked about some alkyne chemistry. So alkynes react like alkenes, except when it comes to the Lindlar catalyst and when it comes to the fact that you can deprotonate them. They do other stuff too, but it's beyond the scope of the course. So I think that's where we're going to leave SN1, SN2, E1, E2. Next class, we're going to briefly touch on oxidations. And then we're going to move to just looking at oxidations from the concept of an E2. And then we're going to start radical chemistry, which is not as exciting as it sounds. Okay. Thanks, everyone. It's Wednesday. Have a good Wednesday afternoon.